record. Yeah, so this is the one I was saying we've already done this kind of problem, but it really can be thought of as a systems of equations problem, where one equation is the basic perimeter formula with some numbers plugged in, and the other one is an equation that describes a relationship between length and width. So on your own, you know, to begin with, you want to be able to write those two different equations, and we'll talk about how do you want to solve it. So hopefully you're on your way here. If I'm writing a perimeter equation, remember our basic formula, the perimeter is equals twice the width plus twice the length. I'm told the total already, so I can say that 60 equals twice the width plus twice the length. That's what we're hoping for the first equation. All right. Now, the second equation is that relationship between length and width that earlier in the term we just plugged in right away. But here it says the length is 10 more than the width, 10 more than the width, right? So the length is 10 more than the width, width plus 10 or 10 plus W. If it was less, of course, it'd be W minus your number. You got the order matters for subtraction, right? So there's a system for this problem. This is one, it shows up, I think, in the context of our substitution method that we talked about yesterday. This one's already solved for L, which makes that expression, it's pretty easy to just put up in there instead of the L. And we go from there. All right. Just to follow up, finish up, right? I can say then 60 is 2W plus 2 times this whole expression. All right. Distribute, whoops, come on. Right? I'm going to combine the W's. Subtract the 20. 40 is 4W. I guess W must be 10, huh? All right, with that. And find the length and the width. So the length is my width. So it must be 20, whatever units we're talking about. So yeah, 2 of those is 40, plus 2 of those is another 20. 40 plus 20 is 60. You have to catch up. Okay. So the perimeter usually gets something like this. You know, could be, you know, 3 times the width plus 5 or minus 5 or something. You know, we get some expression where we describe usually the length in terms of the width. Makes it a pretty good choice for a substitution problem. Got another one for you here. I'm tired this morning. All right, here we go. Making a snack mix. Of nuts and pretzels. And just taking this one from a problem here on paper, I'm gonna get the good numbers here so it works out nicely. Let's see. Using twice as much pretzels as nuts, and total is 45 ounces. How much of each? All right, so there's a little trick in this one, which is more a difficulty in here that I purposely do this one. So first of all, I'm gonna be real good here, and I'm gonna define my variables. I'm gonna say let P equal amount of pretzels, okay? And I'm gonna let N the amount of nuts. So my variables stand for the quantities, all right, in ounces, all right? So I want to get two equations out of this problem. This is not an unusual form. I've got two different kinds of things. On the one hand, I know if I just combine them, I get a quantity total. But then there's a second relationship kind of relates one to the other, or maybe it's based on their value. So if I know the total is 45 ounces, there's your first equation, really. I know my quantity of pretzels plus my quantity of nuts, it has to equal that 45. There's your basic, one half of all these kind of mixture problems. Now the other one is a relationship between the amounts of nuts and pretzels, kind of like the length and width things. But you're going to use twice as much pretzels as nuts. Can you write a equation that compares the quantity of pretzel to the quantity of nuts? P equals so many N, or N equals so many P, or something like that. And think about it carefully. Twice as much pretzels as nuts. All right, so here I'm going to show you, it always happens, there's something about the way that sentence is written. Oh, twice as much pretzels as nuts. So 2P is equal to the amount of nuts. That's wrong. Think about it again. The amount of pretzels is twice as much as the amount of nuts. Twice as much pretzels as nuts. The amount of pretzels is twice as much as the nuts. It's opposite of what I think is often the first reaction. So you gotta, if you run into a phrase like that, don't rush to write your second equation. Think about it carefully. What's it really saying? The pretzels is twice the amount of nuts, or is the nuts twice the amount of pretzels? The pretzels is twice as much as the nuts. So that's the little problem within the problem there. You got to watch out for that. Okay. Well, here's my system now. Again, this is solved for P, just the way I wrote it. Makes it another good substitution problem. All right. So I get 2N plus N equals 45. 3N is the 45, so the N must be 15 ounces in my problem, right? 15 ounces of nuts, and the amount of pretzels is twice the amount of nuts. So that'd be 30 ounces. Typical word problem for this section, this chapter. Let's go in here. All right. Well, that was just to get us going and think about a couple applications. Get us started here. Can I erase? All right. So those were both a couple examples of applications where the substitution method works pretty well. plug that one expression into the other equation. Our section today, 5.3, is referred to as the elimination method. Or sometimes called the addition method. Sometimes called the addition method. You're going to see we're going to end up actually adding equations together. Oh, so sort of abstractly saying, let's say I have an equation where this expression equals that expression. And I've got another equation that says this expression equals that expression. Well, if those two things are equal to each other, and those two things are equal to each other, if I just add, I still have an equivalency. I still have an equation that's balanced. It's true. If that's true, and if that's true, then if I add those, then it should be the same as adding those. Well, okay, so what? That's sort of the theoretical background there. Here comes the system, right? Two x plus y equals 10, and 3x minus y equals 20. Find x and y, as always. Well, if all this equals that, and all this equals that, on previous presentation said, I could just add them together. Look what happens. Why is this helpful? Well, I'm going to add the like terms, add the x's to x's, and I'm going to get 5x's. But here's a plus y and a minus y. They go away. Don't forget to add the other side. By adding, I've eliminated one of the variables. Now, of course, as always, got to go back and plug it in. If x is a 6, let's say 2 times 6 plus y equals 10. I'll subtract that. Y is a negative 2. Adding them so that you get one of the variables to cancel itself out or eliminate itself is the gist of this technique. Right? It works nicely, mostly, with systems that are built out of two of these standard form equations, right? X's and Y's on the same side. Of course, you got to add X's to X's and Y's to Y's and numbers to numbers. You got to move things around because they're mixing it up on you. You got to move them around. Okay, that looks too easy, right? And nobody else trying to come in today. Well, so another one, kind of like that. If you're lucky, the problems will start with one of the variables ready to cancel itself out. Basically, we would like same coefficient, right? This is a 1 and a 1, and opposite signs. That's what we're looking for. Same numbers on one of the variables and opposite signs so that we add, they cancel it. I get 3 x's, the y's go away. And that's simple enough, I just do that. All right. Plug it in, let's find the other, I'll use this one. 3 minus y equals 4. Subtract the 3, negative y is 1, so y must be negative 1. That's the nice one. The numbers, the variables are ready to go away. From here on, we step it up and we make them ready. We make the numbers the same so that one will cancel out. How do we do that? Well, we're going to multiply one or both of the equations by whatever is necessary to get the numbers to be the same. So let's say this one. Here we go. 4x minus 3y equals 1. And let's do 5x minus 9y is a negative 4. Funny looking for, but oh well. Well, all right. You can just think about that. Gee, if I tried to use the substitution method, that'd be pretty messy. Trying to solve for y, I'd be dividing by 3, and I'd get fractions all over the place, or about the same as with x. So here's where this particular technique is often the preferred technique. Well, but they're not the same numbers, right? To begin with, not the same size, absolute value. Well, so we're going to look at these and say, well, which one would be easiest to turn into the other one? Like, I'm looking at the y's again here and say, well, I could multiply this entire first equation by 3 and turn that into a 9. And in particular, they're both negative. So how about if I multiply everything by negative 3, it'll be positive 9. Okay, that's what I'm deciding to do. I'm going to multiply the entire equation, and here, my parentheses to emphasize distributing, I'm going to multiply that entire first equation by negative 3. I'll go with my arrows again. Negative 3 times 4x gives me negative 12x. Negative 3 times negative 3 is positive 9y. And don't forget the other side, negative 3. There. I modified, I changed that first equation to this one. Same, proportionally bigger, same balance there. But now the y's will go away again if I add them together. So here that gives me negative 7x. The y's cancel, negative 7, I guess x is a 1. And always, got to plug it in someplace. Let's say, I'll go back to the original up here and say 4 times the 1 minus 3y equals 1. So that's a 4. I subtract 4. Negative 3y is negative 3. Y is also a 1. Sometimes you get lucky and the variable's ready to cancel itself out. Here's the next level where I've got to multiply one of the equations to get those coefficients to be same size and opposite signs. You could technically subtract one from the other, but you imagine minus minus a minus, we'd make more mistakes if we were subtracting. So we try to get opposite signs so that we make fewer mistakes adding. Okay. 3x plus 2y equals 2. And apparently 6x plus 5y equals 8. Similar situation. Not really ready to go yet. None of them are going to cancel right away. So we need to multiply one or the other of the equations to try to get the same size numbers or coefficients. All right. Well, all my examples so far have kind of worked with the y, but look at here. I could turn the x's both into 6's pretty easily. So again, I'm going to take this first equation and I'm going to multiply it by 2, in particular a negative 2, to change the sign. Negative so that I get minus 6 to go with this plus 6. Don't forget the other side. Okay? And so that becomes negative 6x minus 4y equals -4. Ready to add them together. The x's cancel, and I have only one y left, equals 4. Okay? Always, almost always. So what's that one example yesterday where you just wanted the number of policies, but almost always we have to find both variables. So y is a 4, I'll use the first one just because it's smaller numbers, totally arbitrary. 2. All right. Subtract the 8, and I get 3x is -6. Divide by 3. X is a -2. -2, and the y, whoops, y was a 4. All right, that's nice. Good enough. Huh? Here we go. Yeah, all right. Step it up. Next level. So 7x plus 8y is 4 equals 4. 3x minus 5y equals 27. I can't just multiply one of the equations and easily turn it into the coefficient in the other. I don't want to multiply by 2 1/3 or whatever to turn 5 into an 8. So I need to find the least common multiple, like common denominator. What's the smallest number I could turn them both into? And now I have to look and say, do I want to? Well, let's see, I could turn these both into 21s, or I could turn those both into 40s. I think I'll go for the 21s. Okay. So I have to multiply both equations. That's what the point is this time. Both equations. So this one's getting multiplied. Let's do it by 3. And this one, let's do it -7. The plus minus doesn't matter which one you choose, but I'll get opposite signs that way. Okay. The least common multiple I've chosen is 21 over there for x's. All right, so rewriting them both. Here I go. 21x plus 24y equals 12. Ooh, I'm gonna get a big number over there. Oh well. Here I go. -21x minus minus is plus 35y equals, all right, here we go. 7 times 27, 49, 14, 189, and minus -189. All right, now I'm ready. X's cancel themselves out. I've eliminated the x's. But here I'm going to get what? 59 y's equals 189 minus 12 is 177 negative. Bigger negative number, right? All right, divide by 59. Do that in your calculator, but it's -3. All right, 3 times 60 would be 180. Well, there's that x, that 3 less there, so that's a little not too tough mental math. Estimate, guess, and check, and then you can multiply out. But using your calculator, you get there. So now I got to find the x. I don't really want to use the bigger numbers this time. Yesterday we were saying, oh, if I've changed one solve for x, you could use it. But I'm going to go back on one of the original ones here. Let's say 3x minus 5 times -3 equals 27. 3x plus 15. 27. Subtract that. 3x equals 12. 4. X is 4. Y was negative 3. So that's, well, almost the highest level of complication, but that's, as complicated as the technique, basic technique gets, is having to multiply both equations to get similar size coefficient there. All right. Here we go. Now, if we were doing homework problems out of the book, you'd see some of these. But I think mom is being nice to you, or we've been nice to you with the problems we've chosen for mom. And I don't think you're going to run into fractions like this, but it's something we should practice. Think about anyway. So here's a system of equations, just happens to be built out of fractions. Bug. Well, like we have done before, let's just get rid of fractions first. And then we look at it and start over. So our first step here is get rid of fractions that has nothing to do with solving it. Right? Nothing to do with really solving the system yet. I can look at each equation individually. Here we call our technique, it was let's multiply everything by that common denominator. That's going to allow the fractions to reduce to integer values. So 3 and 2, I'm going to multiply everything by a 6. Okay, I'm going to multiply everything by 6. Now over here, I'd get 6/3 x minus 6/2 y equals 6. First equation, right? Just 6 on top, 6 on top. Here I go back over here. That's 2x minus 3y equals 6. I'm just getting rid of fractions. Similarly, for the second equation, now common denominator, how about the 4? I just multiply everything times 4. Here that would be, let's say, I'll write it all out, right? 12/4 x minus, I got to multiply the whole number too, 4y, and here I'd get 20/2. I'm just showing all the scratch work, you might say. Now I'd reduce those fractions. Here I get 3x minus 4y equals 10. There now is an equivalent system without the fractions. And now I start with, what technique do I want to use? Well, substitution might not be too bad with the first one, but that is solving for x or y, but we're practicing our elimination method. I can turn those into 12s or turn those into 6s. How about we go for 6s, okay? So I'm going to go this way this time. If I multiply this all by 3, all right, I'm going to get 6x minus 9y equals 18. So I'm going to multiply the second one by a negative to get negative 6. I'm going to multiply by negative 2. Negative 6x, negative is plus 8y is negative 20. Ready to add them together? Negative y is what's left equals negative 2 because y equals 2. Multiply both sides by negative 1. Right. Now I have to find the x value. Well, it wouldn't be too tough. I could put it in 1/2 times 2, but I don't need to use the fractions. I could use one of these. It's an equivalent equation. I would suggest that, right? let's use one of these where we already got rid of the fractions. So if y is a 2, let's say 2x minus 3 times 2 is 6. And so 2x minus 6 equals 6, add 6. 2x equals 12, x is 6. 6, 2. The point of that one was just getting rid of the fractions. Okay? Getting rid of the fractions. All right. Moving right along. Yeah. All right, let's see. Five x minus 3y equals 15. Y equals negative 5 plus 5/3 x. Uh-oh. I really mean this example? Well, that's not standard form. Can't really use elimination right now. I think I'll rearrange it, okay? I'm going to rearrange it. So I'm going to, let's subtract the x's. All right. Because we usually put the x's before the y, I'm going to start with negative 5/3 x plus y equals negative 5. Still just working with that second equation. And now, like the last one, I'm going to multiply everything by a 3. Let's multiply everything by a 3 and get rid of the fractions. So here it cancels off. Negative 5x plus 3y equals negative 15. Finally. Now, that was all the second equation. Let's bring down that first one. Oh, 5x minus 3y equals 15. Do you see what's happening here? Add them together. That's why that was messy. They hit it. What does that mean? 0 equals 0. Yeah. True. Always true. Dependent, otherwise known as same line. Infinite number of solutions. All right. And evaluate any xy pair that makes it's one line, an infinite number of points on that line. Right? So all that work to get down to, well, the elimination method shows us similar result to what we came up with some of the substitution problems and our graphing problems. You know, sometimes you get no variables left, and it's always true. So that represented the same line. Okay. And, you know, like I said, they had to kind of hide it, make it a little messy. Again, these are examples I pulled out of the text. All this online stuff, we're just using the things we programmed in the MOM. Not always as rigorous where we sometimes put that. How about this? Negative 3x plus 2y is 8. 9x minus 6y, 13. What's this one going to be? I'm so predictable, I think. Well, I can multiply by 3 and I get 9s here, right? So let's multiply that first one. Everything by 3. I get negative 9x plus 6y equals 24. Add them together. No x's, no y's. 37. New math. 0 equals 37. Here's that classification word, negative, inconsistent. So again, our elimination method can show us that same kind of result, can show us an inconsistent result there. No solution. And you can just see by multiplying by 3, even if I did switch signs now, this equation, the numbers, the x's and y's are just multiples of each other, but different number on the other side. Okay. All right. Yeah. The sum of two numbers is 65. Their difference is 25. Find the numbers. I have two different sets of conditions, so I'm going to write two different equations. Let x be one number, let y be another number. Defining my variables, choose a couple variables I need to represent them. Just the two numbers, the sum is 65. Hopefully that's easy. If I add them together, they add up to 65. Similarly straightforward. The second one, their difference is 25. If I subtract one from the other, I get a 25. That's nice. The y's are going to go away. 90. Yeah. X is 45. Plus y equals 65. If I subtract the 45, I think I get a 20. Yeah. Now, this is not technically an ordered pair problem, but find the two numbers. One number is 45, the other number is 20. Say something like that. If you were writing a sentence, written application problem solution, something like that. Okay. And how about this one? So they kind of call that a number puzzle, just relationship between two numbers, and they give us two different relationships between those numbers. How about sodium, salt, right? And 2 hot dogs, everybody's favorite. Yeah, I hardly ever eat those. I like sausage, but hot dogs. And 3 cups cottage cheese. Don't eat that much either. Please do. Sodium in 2 hot dogs and 3 cups of cottage cheese is 4,720 milligrams. Okay. And let's see. 5 hot dogs and 2 cups cottage cheese is 630. Whoops, 6,300 milligrams sodium. How much sodium in hot dog and cottage cheese? How much in each? So slightly compressed verbiage there, written out as a paragraph in a textbook problem. But let's see, let's let H be sodium in a hot dog. And let's let C be sodium in cottage cheese. Okay. Now I want to write a system of equations based on, these are two different situations, right? I'm going to sort of squeeze them in first and then kind of erase the words so I can work the problem. So I have 2 hot dogs. So the amount of sodium is 2 times the H value. Whatever sodium's in one hot dog, it's going to be 2 of those. So I got 2H plus 3 cups of cottage cheese. And so I'm letting C stand for the amount of sodium in that cup of cottage cheese. So I've got 3 of those. And apparently that adds up to 4720. See how that works? 2 times the amount in that plus 3 times the amount in that, and it adds up to some total. Similarly, this one, well, 5 hot dogs, 5 times the amount in a hot dog plus 2 times the amount in the cheese, 6,300. So there are my 2 equations. I'm going to put them together and pick a way to solve it. You allow me now? All right, I'm going to erase the words so I can just play with the numbers again. Okay, I'm going to leave this over here for a second. So what did I have? 2H plus 3C equals 4720. I purposely chose, letters that kind of related to the problem. Watch out for that in Mom. They might tell you to use a certain letter. That happens, right? All right, so here is my system written side by side. Well, again, substitution would be kind of messy. I'd probably get some fractions in there somewhere. So I'm going to try the elimination method. And even graphing is real iffy. Unless you got nice small numbers, and if it didn't line up right on intersection, you're kind of guessing is it 5.5 or whatever. Not the preferred method, but anyway, so substitution or elimination is what we usually use. How about, I'm going to turn them into tens, okay? I'm going to make this 10, so I'm going to multiply this by 5 and this by -2. You could have chosen to go to 6s. It's not a whole lot different. So here I'll get 10H plus 15C and 5 of that. Let's see, that's still 0. That's 10, 35, 36, 23. You do that in your calculator if you want to double check me. -2, -10H minus 4C equals 2 of those is going to be 0, 0, 6, -12,000. Now I'm ready. 11C is what's left here, right? And plus minus, that's kind of nice. So 0, 0, 6 minus 6, 0, 3 minus 2 is a 1, 1. 11 cups is 11,000. I guess 1 cup of cottage cheese is 1,000 milligrams. Watch out for units. And here, the fact that I'm using C stands for the sodium in a cup. So C is at 1,000 milligrams. Now I got to go back and find how much is in a hot dog. Pick one of the original ones, smaller equations, right? So let's say 2H plus 3 times 1,000 is my 4720. That's 3,000. If I subtract the 3,000, I get 1,720. Okay with that? 3,000, I subtracted 3,000 from both from this. It was pretty easy mental math there. Dividing by 2, 1720 divided by 2. And what is that? 8, 6, 860. So the amount is 860 milligrams. Do you believe it? A hot dog's got fewer milligrams than a cup of cottage cheese. Boy, look at those packages of hot dogs on the amount of, it's the fat ratio. Some hot dogs are like 75% fat, but you need the sausage cheese fat. Oh well, enough of that. So here is, again, an application problem, right on time, good, where we've had two different sets of conditions based on a quantities amount of something, how many of that type of thing. And the elimination method was pretty well there. Okay, that's going to be it for today. That's section 5.3, where we practice the elimination method. Our last section, 5.4, is more applications. I'm just going to do more of this tomorrow. Roll out a variety of applications of practice, a couple different other varieties, you might say. And so, next week, that leaves next week, Monday and Tuesday, for a little more of whatever and reviewing, and the test planned for Wednesday next week. This is the end of the main concepts in the chapter, and now we practice some more applications. So, get your homework done. I hope you noticed my note in the forum yesterday, we're in week 9. Week 9 plan and homework is another equation, another problem like last chapter, chapter 4 application. And so I opened up the week 10 hand in homework because those are the couple systems problems. And I encourage you to look at those. They're applications, kind of like we're going to practice here. And look at those before test day next Wednesday. All right, folks, have a good rest of your day, and see you tomorrow.
See you tomorrow. Thank you, Steve.
Okay, you're very welcome. See you later.